Okay. Now there's a bunch of physics here, and unless you happen to be in the physics class, and only one member of the linear algebra class is in the physics class, the rest of you hopefully will be in physics next year. We can do a bunch of physics with energy conservation and other things, and we can derive the proportionality between dy dt, and you're taking calculus, so you know dy dt is the rate of change of y with respect to t. Y is how far the water level is above the hole. Dy dt is the derivative of y with respect to time. That's how fast the water is descending at any given moment, y being a function of t. And this changes, of course, as the depth changes, dy dt is going to change because the water goes out more and more slowly. The question is, how's dy dt related to y? Well, there's where you do the physics, and then there's mathematics involved here. At the end of a first semester calculus course, once we've figured this relationship out, you'll know enough to actually derive the fact that, at least from this relationship, you won't know how to use energy conservation and so forth, but once we have this relationship, you'll be able to easily derive the relationship that shows you that y is a quadratic function of t, which of course is something we've been assuming. Okay, so y is a quadratic function of t. Now, we can analyze that data. At this point, we haven't gotten to a point where we can actually use linear algebra to get the best fit possible for the data points, okay? And that's something that we're going to end the semester on. That's a very neat idea, and it incorporates most of the stuff we've been doing since the first test. But that's what we're heading toward. We're not there yet. So where we are now, and what I've asked you to do so far, is simply pick 3 data points, and everybody picked 3 different data points because you've got 5 to pick from, and calculate the values of A, B, and C. And that's very easy. You take the 3 data points, everyone gives you a y and a t, so you plug the y value and the t value for one data point, the y value and the t value for another one, and a third one, and you get 3 simultaneous equations in 3 unknowns that you can solve using inverse matrices or matrix reduction, augmented matrices, in many different ways that everybody's pretty good at. Okay, then that's good, but that's not the best thing to do. That's all we've done so far. Okay, a better result is obtained by analyzing the data, but first sketching a graph for all the points. Okay, and then we sketch a smooth curve, and we do this graph on graph paper, so we make a pretty nice graph. Okay, we sketch a smooth curve, and then we pick 3 points on the curve, not 3 data points, 3 points on the curve. The curve is going to represent the actual trend of the data. The data points all have little errors in them. If we get the curve, we smooth out the errors. And so using the curve, we pick 3 points, y versus t, and then we get our 3 equations from points on the curve, not from data points. Now, this is, and I sketched this, of course, already for another class. If here's your data point, here's a data point, here's a data point, I think here was a data point, and here was a data point, right? Now, I have 2 possible curves. Okay, one curve goes through every data point, but the data points all have little errors. Now, the trend of the data points, they keep getting lower and lower, and they better because y keeps decreasing as t increases. The white curve represents, or is an attempt to represent, the parabolic curve that best fits these data points, or that indicates the trend of these data points. Okay? The orange curve is a curve that tries to hit every data point. Now, which one of these curves is more representative of what actually happens when the water flows out of that tube? Well, it's not this one, because the lower the water gets, the slower the flow. You can see that very easily, and everybody pretty much understands that even before they see it. After having seen it, you know that's what's going on. Now what's happening here? It's going down fast. Now it's slowing down. Well, that's what it's supposed to do. Keep slowing down, but then it speeds up again. Graph gets steeper, meaning that the water's flowing out faster now, that the depth is changing more quickly. Well, that doesn't happen. This is the model. So we take our data points, like on a graph here, and we pick 3 representative points. Not 3 points just on this section of the curve, not 3 points just in this section of the curve. 3 points that are kind of well spread out, 3 points that we're pretty confident indicate the trend of the curve. Now there's an art to picking those points, there's actually science to picking them, and we're not going to worry about that. That's beyond the scope of what we can do right now. But we pick these 3 points and we plug them in and solve to get our A, B, and C. That's our next task. And then our final task is going to be to take all 5 points and figure out what the best possible quadratic model is. And then we run this back to the physics class and tell them, hey, confirm this for me.